Hello everyone, my name is Kisung Kim. I am the CTO of BitNine Global. In this session, I'll present BitNine's new graph database solution called AgensGraph. Graph database is a change in the data representation. Gartner says that it is a radical change in how data is organized and processed. Let's compare the graph model and the relational data model. In the relational database, every piece of data is a row. The data is managed as a row of a table regardless of whether it is an entity or a relationship. If we want to retrieve some pieces of data from the database, usually we would join the related tables by ourselves. The database does not provide any facilities to handle relationships. But the graph model uses nodes and relationships rather than rows and tables. The relationship is the first-class citizen in the graph database. This is the biggest difference of the graph database. Relationships are explicitly managed and handled directly by the database engine. In the graph database, you can create nodes and relationships explicitly, and you can query in terms of them. So you can make your data more connected, and the management of the connected data becomes much easier in graph database. The benefits of graph database can be summarized like this. By changing the data representation, data modeling can become more intuitive and simpler in the graph database. The ER diagram can be used for the data modeling directly. And the graph database provides a very concise query language like Cypher and Sparkle. Queries are described using graph patterns. So we don't need to specify any join in a graph query. As a result, the query can be concise and easier to create and maintain. The graph database is optimized to provide the optimal performance for graph pattern matching, which is generally not optimal in other databases. And graph database provides a new kind of data analysis method, graph analysis algorithm in the database engine, like PageRank, shortest path, and graph clustering. Let's see how graph modeling becomes simple by an example. In this example, sellers have their products and customers order these products and rate them. If we represent this as a relational model, we will make a table for each entity and relationship. The order table has the information who bought which product. So the order table stores relationships between customers and products, but in the viewpoint of the database, it is just a table. In the graph database, this real-world model is reflected directly to the graph model. The relationships between entities are stored as relationships in the graph database. So you can see that the data model of the graph database is much simpler than the relational database. I want to introduce Cypher query language to show the conciseness of the graph query. Cypher is created by Neo technology. It is a declarative query language for the property graph model. It is inspired by SQL and Sparkle, which is the standard query language for RDF. It borrows many clauses from SQL, such as where and order by, and it borrows the graph pattern matching features from Sparkle. Neo technology opens the Cypher language specification as a public project, OpenCypher. So other vendors can implement the Cypher language in their own database system. Let's see how a Cypher query is concise using this example. This is an example of SQL and Cypher query to find all ancestor and descendant pairs in a graph. In SQL, we can use the recursive common table expression to express this kind of queries. And we have to specify how to retrieve the relationships using joins and CTE in the query. So as you can see in this example, SQL is not so simple. To find out what this query means, we have to review and interpret all this code. But in Cypher, this kind of relationship can be expressed in an intuitive form like this. The graph pattern is described using an ASCII code diagram. So it is much easier to read and understand the meaning of the Cypher query than the SQL query. Recently, the graph database is getting more popularity. There are many graph databases already, and existing database vendors like Oracle and SAP, IBM, they start to provide graph features in their products. Even no SQL database vendors like MongoDB and Elasticsearch start to provide graph features in their database systems. As you can see in the previous slide, there is a broad spectrum in the graph database area. They have different graph model and architecture, graph query language, and target workloads. Some database supports the property graph model, and others support RDF graph model. And some systems support ACID and OLTP workloads, and others support only graph analytic workload. What we want to implement is a graph database which provides the property graph model, Cypher query language, ACID transaction, and both of OLTP and graph analysis workload. We chose to implement a graph database based on PostgreSQL because it has already great features we need, like a storage engine, transactional layer, and cost-based query optimizer. Of course, each model should be enhanced for graph workloads because PostgreSQL is a relational database. But PostgreSQL gives a good starting point. We released AgensGraph version 1.1 recently. It is a forked project of PostgreSQL for the graph data. PostgreSQL has an excellent extension feature, so we considered to develop it as an extension module of PostgreSQL. But we cannot develop it as an extension because we have to modify query parser and add some plain nodes for graph processing. So AgensGraph is developed as a forked project of PostgreSQL. You can visit our homepage to download our AgensGraph, and AgensGraph is an open source project which is distributed under Apache license. So you can clone the source code from our GitHub. From now on, I'll explain some features of AgensGraph and how we implement it based on PostgreSQL. AgensGraph supports the property graph model and JSON document. The property graph model consists of vertex, edges, and their properties. The vertex and edges can be grouped into labels. For example, you can make vertex labels like persons, student, and teachers to distinguish vertexes. We extend this property graph model in two ways. First, we extend it for vertex and edges to have JSON document as their properties rather than key-value pairs. These properties can be indexed using any kind of indexes PostgreSQL provides. This is one of the great benefits from developing based on PostgreSQL. And we introduce label hierarchy for property graph model so that you can organize these vertex and edge labels in a hierarchy. AgensGraph supports multiple graphs, so you can make several graphs in a database. Before I show you an example, I'll introduce more details about Cypher. Cypher has various clauses. Some of them are borrowed from SQL, and their meanings are familiar with you. For graph pattern matching, you can use match clause, and for updating the graph, you can use create, merge, and set clause. This is a railroad diagram for Cypher syntax, and you can make a query by chaining these queries as you want. I'll show you an example about this later. This is an example of AgensGraph DDLs. We provide DDLs to create graph objects, vertex, and edge labels. You can make graph like this, and using create graph DDL statement, and you can make vertex and edge labels. In this example, we made one graph object and 3 vertex labels and 2 edge labels. If you want label hierarchy, you can create a label using inherit keywords. And then we can make vertex and edge objects using Cypher queries like this. The first query makes a vertex whose label is person, and its properties are described using JSON format like this. In this query, there are 3 properties: ID, name, and company, and their value is Won and Kisung Kim and BitNine Global. This query makes a vertex whose label is person, and their property values are like this. And then we made 2 more vertexes using create queries. One is for community, and one is for conference vertex. So we made 3 vertexes in this example. After that, to check out these vertexes, we used the match query. In this match query, there is a single node pattern, which is described by omni A. And so this match query returns all vertexes in the graph. And in this graph, there are 3 vertexes, and we can see that in this result. And then we can create property indexes for some interesting properties like this using create property index statement. And the first one is create a property index on vertex label person, and this statement make property names ID. And then the following 2 statements also create property indexes on conference and community. And then you can create relationships using Cypher match and create like this. To make a relationship, we first have to find the vertexes to be connected. So we use match and create clauses in a single query. This example query first finds vertexes to make a relationship among them. And the next clause, create, indicates to make relationships between A and B and A and C. And then we can check the relationships using this query. Like the previous one, we use match clause, and we can find that there is a attend and related relationship between these. I'll introduce the architecture of AgensGraph. AgensGraph is not a layered architecture. Rather, it is developed at the core level of PostgreSQL engine. We implemented the graph objects and designed the storage layout for the graph data. We extend PostgreSQL's query engine to process Cypher query. To implement it, we modified the query engine, including parser, optimizer, and executors. But we tried to integrate Cypher with the SQL query engine seamlessly. We maintained the storage and transaction layer of PostgreSQL, so most PostgreSQL's external modules and extension modules can be used with AgensGraph too. This is the graph storage layout of AgensGraph. We use heap tables to store graph data and use B-tree index to index edge and vertex ID information. The heap table for the vertex has two columns, vertex ID and properties. And edge tables has four columns, edge ID and start and end vertex ID and properties. There are two composite indexes for edge tables, start end and edge end start. We built two indexes for edge tables to find all incoming edge and outgoing edges for specific vertex fast. We use composite index to exploit index omniscan for graph traversals if possible. We have not implemented a special storage engine for the graph data, not yet. We found that this storage layout works well for medium-sized graph data. But we also have a plan to implement a special storage engine for the graph data to handle large-scale graph data. And Cypher query is processed in the same way, in the same query engine with SQL. It is processed from parsing, analyzing, planning, and execution. We integrate Cypher query processing with the SQL engine from the parser to the execution engine. So any PostgreSQL expression or functions can be used in a Cypher query where it is allowed. And any query optimization techniques applied for SQL can be also applied to Cypher. This is a huge value from using the relational engine. And this can be possible because the result of Cypher query is also a relation. We treat a Cypher query as a subquery so that after analyzing pace, Cypher and SQL is identical and processed through the same logic. As I already mentioned, in Cypher, several clauses can be used in a single query. Basically, each clause makes result from, and the following clause read the result and process them. When processing a Cypher query, first the query is transformed into a query tree structure. To make a query tree, first each clause is transformed into a query structure. The query structure is an internal structure of PostgreSQL. For match clause, it will be a query with join tables, and the chained queries are combined as subqueries. Let's look at this example. This query is composed of three clauses, two match clauses and one return clause. So the first match clause is transformed a query with three tables as an input. In this case, to process the first match clause, actor table and xin table, movie table will be joined in a single query structure. And this query structure becomes an input to the next query structure of the second match clause. And this diagram explains this. The outer query structure is the second one, and inner query structure is the first one. So internally, we create a query structure like this in a nested form. So in this diagram, we can see that the first match clause becomes sub-query to the next match query. After we make this internal query structure, the query optimizer of PostgreSQL tries to optimize this query structure. And in this case, there are query optimization techniques called sub-query rollup. The sub-query rollup technique make nested sub-queries into one query structure. In this case, this inner query structure can be rolled up to the outer query structure, and the final result will be like this. Only one query structure. Because I show this internal example to show that we can exploit internal query optimization techniques of PostgreSQL to processing Cypher queries too. And we implemented some new plan nodes for improving the graph query performance. As an example, I present VLE plan node, which is variable length edge plan node. VLE pattern is concise way to express a range of matching paths. This query can be implemented using recursive common table expressions, as we saw in the previous example. But we found that the CTE approach has some performance issues. The CTE approach is a breadth-first search approach, which needs to buffer all intermediate results in memory. So, to improve the performance, we implemented a new node for this, which performs depth-first style processing and need no buffering. This is an example of execution plan for this Cypher query. This query uses VLE length edge patterns like this. And so you can see that there is a new plan node whose name is nested loop VLE. This node conducts graph traversal using depth-first search fashion. There are many considerations about graph query processing. Among them, I want to explain 3 points here. First, graph pattern matching is usually more efficient to use random page leads rather than sequential leads. So it is recommended to decrease random page cost parameter value, which is Postgres configuration parameter to set the cost of random page I/O. The graph processing uses random I/O extensively. It is more efficient to cache the data in memory or use SSD storage to store the graph data. And we design the edge index to use index omniscans when it is possible. When traversing the graph, edge indexes are used, so it is more efficient to use index omniscan. And finally, the query optimization is crucial for the graph query processing. But usually, it is harder than SQL queries because graph queries involves many joins. We found that PostgreSQL's query optimizer works well, usually even for graph queries, but it needs to be improved more, and we need more research on them. And I want to show the performance comparison. We conducted a performance comparison using LDBC benchmark tool. LDBC is a consortium for making a benchmark tool for graph workloads. There are big companies to participate in this project like Oracle, IBM, Huawei, and SAP. There are 3 kinds of benchmark workloads. The first one is social network benchmark called SNB. This one simulates the social network service like Facebook. In this benchmark, users create friendship and write posts and comments, and they can like the post or comments of their friends. It is a OLTP workload and similar to TPCC benchmark. And there are graph analysis benchmark which conducts large-scale graph analytics. We use the SMB interactive workloads for the performance comparison. This is the result. We compared AgensGraph version 1.0 and Neo4j 3.1, the newest one. I want to emphasize that even though we had optimized 2 databases as much as we can, the result can be changed in any time according to the server configurations. For now, the result shows that AgensGraph is much faster for updates and complex queries too. And notice that for this chart, the y-axis is log scale. For updates, the results are because of the efficient concurrency control of AgensGraph, which exploits the MVCC model of PostgreSQL. For the complex queries, AgensGraph is better than Neo4j for most queries. There are many things that improve AgensGraph performance. Those include more optimal query plan and more advanced query execution method. We can even optimize the graph query performance by using Postgres advanced features. And I'll conclude my presentation with our future roadmap. We plan to extend AgensGraph for distributed and parallel systems. So we are currently considering Postgres XL project, which is shared nothing extended database of PostgreSQL. And we'll implement graph analysis framework like vertex-centric programming model. We are also considering integration with big data system for large-scale graph processing. And this is the end of my presentation, and thank you for your attention. And do you have any questions? Yes, we have tools, and we can use any tools which migrates from other database to PostgreSQL too. Yeah, and then we can use Cypher queries to translate relational tables to graph data. Oh, okay. Yeah. Your opinion for the graph database?